Lastly then, we want to take a look at some geometrical properties of the cross product. And we'll start by looking at a parallelogram that's formed by two vectors. Remember that any two vectors form a parallelogram. So let's suppose I've got a vector here A and another vector here B. So again, I can form a parallelogram by drawing a copy of B off the tip of A and a copy of A off the tip of B, and we have this parallelogram here. Now what's the area of this parallelogram? Well, the area is equal to the base times the height of a parallelogram, which is equal to, well, the magnitude of the vector B, that's the base, we can think about it that way, and the height I could think of as this distance right here, h. So let's think about an angle here, theta. How could I find h if I knew the angle between A and B? So I've got the magnitude of B times h. Well, let's see, the sine of theta is equal to opposite, which is h, over the hypotenuse, which is the magnitude of A. That's over the magnitude of A, right? Opposite over hypotenuse. And so h itself is equal to the magnitude of A times the sine of theta. So the area then of that parallelogram is the magnitude of B times h, which is the magnitude of A, times the sine of theta, which is exactly equal to the magnitude of B cross A. And of course, B cross A has the same magnitude as A cross B. The vectors go in different directions, but their magnitude is the same. So we can find the area of a parallelogram formed by two vectors by taking the cross product of those two vectors. Now, if I take A cross B, we can think about that vector coming up this way. Oh, sorry, this would be B cross A. And so the length of this vector is the same as the area of this parallelogram. Kind of interesting. So there is one geometrical property. So for example, if we wanted to find the area of the parallelogram that had these vertices, say A at 1, 2, 3, B at 1, 3, 6, C at 3, 8, 6, and D at, say, 3, 7, 3. So we could just draw a picture, and we could say we have A here, B here, and I hope these make a nice parallelogram. So what I can do is simply form a couple of vectors. I form the vector AD and I form the vector AB. So I form AD, that vector, which is what? From A to D. So the components of D minus the components of A, that's 3 minus 1 are 2, 7 minus 2 is 5, 3 minus 3 is 0. And I form AB, and let's see, that's from A to B. That's 1 minus 1 or 0, 3 minus 2 is 1, 6 minus 3 is 3. The area then is equal to the magnitude of the cross product of those two vectors, AD cross AB. Now, I'm going to go ahead and let you guys try and find this cross product on your own. What you should get, I believe, is 15, negative 6, and 2 for the cross product. So the area then is the magnitude of that. That's the square root of 15 squared plus negative 6 squared plus 2 squared, which I believe comes out to be about 265, the square root of that. That's the area of that parallelogram there. Okay, so you got some problems like that. That brings us then to a three-dimensional version of a parallelogram, which is called a parallelepiped. Parallelepiped. So this is a three-dimensional object where the opposite sides are parallel, as opposed to a two-dimensional object where the opposite lines, the opposite sides are parallel. Here you have faces, opposite faces are parallel. And so just like any two vectors form a parallelogram, any three vectors that start at the same point, which we can always make happen, we can move our vectors around, form this parallelepiped. Okay, maybe I should just put that on the test, spell parallelepiped. So let's think about this here. We've got, suppose some vector A coming up like this, some vector B here, and some vector C sort of going back that way. So there's A, there's B, and there's C, all starting in the same point. So by making copies of each of these in the appropriate locations, I think you can see what we mean by this parallelepiped here, this three-dimensional object, opposite faces being parallel. And I want to find the volume of this. That's the goal here, and we're going to do it using both the cross product and the dot product actually. Now the volume is going to be the area of the base times the height. So the area of this base here, which is the parallelogram formed by C and B, times a height, which I will call H, and I'm going to put that right here, coming off of this. Okay, so here's H. Now H I can think of as lying on a vector which is orthogonal to both B and C. In other words, I can think of H as lying on the vector B cross C. Okay? Alright, now area of the parallelogram on the bottom, A, what is that equal to? Well, that's pretty straightforward. That's just, as we talked about, that's a parallelogram formed by B and C, so that's the magnitude of B cross C. There's our area there. Now H is going to be, well, what is that going to be? If you think about an angle here, theta, and we've got a magnitude here, let me put A where it belongs. Let me put that right here. So H, if I think about this triangle being formed right here with an angle here, theta, I see that the cosine of theta is equal to the adjacent side H over the magnitude of A. And so H is equal to the magnitude of A times the cosine of theta. So bringing that back over here, putting this in for this H right here, we have that the volume is equal to the area, so I put this in for A, which is the area, the magnitude of B cross C, times A times the cosine of theta. So that times the magnitude of A times the cosine of theta. Let's see. The magnitude of the two vectors multiplied together times the cosine of the angle between them, because this is B cross C right here. Theta is the angle between B cross C and A. Hey, yeah, that's a dot product. Let me write it this way first. A times B cross C times the cosine of theta. That's just simply A dotted with B cross C. And we want the magnitude actually of that. The magnitude here, the dot product gives us a scalar. Here by the absolute value signs, we do mean the absolute value. Make it positive, because if we happen to do B cross C sending that in the opposite direction, we'd have an angle bigger than 90 degrees for theta. We'd have a negative volume, so we just take the absolute value to make sure that it's positive. Okay, this is what's called, well, A dot B cross C is what we refer to as the scalar triple product of those three vectors A, B, and C. And again, the magnitude of that, which by magnitude here we mean the absolute value of it, is the volume of that parallelepiped formed by those three vectors if we start them in the same location. So, just a quick example here. We're going to find the volume of, let's say, the parallelepiped formed by the vector A, which we'll say has these components, 6, 3, negative 1. The vector B, which has these components, 0, 1, 2. And the vector C, which has these components of 4, negative 2, 5. Well, the volume is the magnitude of A dot B cross C. Now, you can take the cross product here and then take the dot product when you're done, but there's a shortcut here. And what I'm going to do is, instead of doing I, J, and K and doing the cross product first, I'm going to put the components of A in my first row, the components of B in my second row, and the components of C in my third row. And then I will just take the determinant of this matrix the way we did before. It'll be 6 times the determinant of this lower right, that's 5 minus a minus 4, minus 3 times, block out its column and row, take the determinant of what's left, that's 0 minus 8, and then plus a negative 1 times the determinant of the lower left, that's 0 minus 4. And we want the absolute value of this, again, make sure it comes out positive for the scalar triple product. So let's come down here to finish this. That's 6 times 9 minus 3 times negative 8 minus 1 times negative 4. So we've got 54 plus 24 plus 4. How much is that? 54 and 20 is 74, plus 8 is 82. And of course, this is a volume, so if we have units given, it'd be cubic units on that, 82 cubic units. So that's a shortcut to find a scalar triple product. You get the same thing if you do the cross product first and then take the dot product. And that brings us to our password for 9.4 to get you into the homework. I know you're dying to get in there and take this assignment, and it is obstreperous. O-B-S-T-R-E-P-E-R-O-U-S. Can mean a couple of things. Marked by aggressiveness is one definition. And maybe a little more common definition for obstreperous is unruly or stubborn. So I don't know if you're familiar with this word or not, but I'm sure you can find many opportunities throughout your day to use the word obstreperous. Good luck on 9.4. Please let me know if you have any questions.